Okay, I think I've all set for lecture 25. So we're 3/4 through and we're firmly into the wavelet filter bank book. And let's see, chapter 1 of that book gives the most basic wavelet, the Haar wavelet and filter bank. And then chapter 4 and 5 is really the heart of the book. So I'll do a little of chapter 1, but also draw right away the description of a filter bank. So this subject, like the whole course, is a mixture of discrete time problems, matrix calculations, because that's what we actually do, and continuous time function problems, which illuminate everything. So let's see, and just to mention again, last time I really covered individual filters, and I'll recap those, which were listed at first as two lectures about filters. So so we're a lecture ahead of the listed program, in other words. So can I recap what we did about filters, some individual filters? And we were interested in low-pass filters, high-pass filters. Generally, they had coefficients h of 0 up to h of n. And the filter was simply a convolution. So the output, y of n, was the sum of these h's times the input at n minus k. That's the simplest algebraic expression, and of course we recognize it as a convolution. It has this magic combination where that index plus that index equals that one, so we identify it immediately as a convolution. In matrix language, it would be a tuplets, or maybe constant diagonal tuplets matrix with constant diagonals, and these of course are the numbers that go down the diagonals, constant diagonals. Everything's in these numbers, obviously. That's what we have to choose. If we want to filter, then we have to decide what are those coefficients. And you remember that the key algebraic step was, because a convolution is a bit messy, in the time domain, that sum goes from k equals 0 to n. I'm dealing here with a FIR filter, finite length filter. This convolution in the time domain, you remember, goes into a multiplication. So if I take discrete transforms of the output, the filter, and the input, then this is the absolutely crucial, simple description. And what is h of omega? So that's become then we use these coefficients in a series, h of k, e to the minus, can I put I, or would you, if everybody votes for j, I'll use j. Doesn't matter, right? E to the minus I omega k. All right, so that's the function that tells everything. And that's the function that we graphed, or at least we graphed its magnitude. It's 2 pi periodic, of course. So if we graph it from minus pi to pi, we've got it. And if it was a low pass, and this is 0, and this is frequency, and if it was a low pass filter, then that meant it tailed way off at high frequencies and was, let's say, 1 stayed near 1, and maybe was exactly 1 if we normalize it, at low frequencies. So this would be This would be a graph of absolute value of h of omega, and it would be a low-pass example. So low-pass filters, well, we can see what happens. At omega equals 0, if we want this thing to be, we want h to be 1, and of course that's just the sum of the filter coefficients. I'll usually call them filter coefficients. A real old-timer, or maybe not so old, would refer to them as taps, which has the advantage of being a shorter word, but sounds a little more specialized then. Okay, and then at omega equal pi, where we want h to be 0, that means that at omega equal pi, this is going to be e to the minus I pi will be minus 1, so that'll be the sum of minus 1 to the kth power h of k. So these are the conditions then for a low-pass filter, and the opposite for high-pass. Okay, that's what we developed last time with some examples. Since that's been 2 weeks, that's probably good to remember these basic facts, among which this is the most valuable. It allows us to quickly say what the filter is doing in the frequency domain. Okay, so what's today's lecture about? It's about combining filters into filter banks. So that's the subject of the lecture, and it's obviously discrete time. And we have in mind, so here's the general picture that I have in mind, that we take the signal x. We do what I'll call a DWT, a discrete wavelet transform, which just means we take the signal and we represent it by a different basis, by some choice of functions, and the signal then, the transform takes the signal and figures out the coefficients in that basis. We've seen that step before. So that's the discrete wavelet transform. That's the analysis step, the analysis bank in the filter bank. And then comes a step that is highly important, but not the subject of this lecture, which is to process these numbers. We hope that they're, if we're really done it right, we hope that a lot of those coefficients are very small, negligible. We can set them to 0. So this is a lossy step, and maybe it's compression, where maybe if we were thinking of this is where we get the compression by taking those numbers, setting a lot to 0, actually sort of putting them into little bins. We hope many of them go into the 0 bin, and then others go into other bins, and so we've lost the last digits. It's like we round it off, but we have but these C hats represent that pretty well, and then we do the inverse discrete wavelet transform to get back to a signal x hat, which is approximately x. So that's our goal. And as always, maybe you remember the 2 criteria for any transform, this one or any other, is to be able to do it quickly. If we can't do it fast, it's not going to win. And we hope that it's good in compression. We hope that compression, we get a good with a good compression ratio, we still get an output close to the input. So So good accuracy, good approximation is the other property. So speed and approximation. Speed and approximation. And of course, they're a little bit competing. I mean, the fastest thing we could do would be to not do any of this at all, and then we wouldn't have any compression. If we work too hard on a very, very selective basis that we can't compute quickly, that's not going to win either. So we're looking for a compromise. And the wavelet transform has turned out to be a very, shall I say, very successful compromise? I think it's fair to say very, but I don't mean to suggest that it's the only. By no means. Or even the final winner. People continue to refine these ideas. But it's become a rather basic construction. And let me describe then how we could combine two filters, a low pass and a high pass, into a filter bank. So now I'm going to draw the discrete wavelet transform. This is now what I'm going to do. So I start with my input X. I send it through a low pass filter, I'll call that H0, and a high pass filter H1. So now I'm going to call the outputs, well, maybe I put a box around those to indicate those are operations. And then we get some output Y, naturally called Y0 of n, and Y1 of n. And X of n went in. Good. Good so far, but, well, have to choose a low-pass filter and a high-pass filter. That's what's and to make a sensible choice, we're going to have to know what we're looking for. But right now, I haven't finished the transform because, far from compressing, I've now got two outputs where I had one input. So I'm oversampling. It's redundant at this point. And we could say, all right. But, and redundant transforms definitely have a place in this transform world. But the neat construction is to go to cut this in half, take half of these numbers. These are C's, and these are C's. These are all coefficients, but we got twice as many as we want, so we take half of those. So there's the operation now called downsampling is simply what produces every other Y0 and every other Y1. And there we have the transform. These are the C's. Those are the C's. These are these coefficients. That's the transform. And you see it's fast, right? Obviously, this is extremely fast. In fact, we won't compute the third component and the seventh component and the first component, the odd-numbered components, because we're going to throw them away. So we really will only compute the even-numbered components after low-pass filtering and the even-numbered components after high-pass filtering. And I mean, a filter is really fast to do. So in principle, we could do the filters. In practice, we do it just straight because our filters aren't that long. I don't have in mind filters of length thousands. But if we had very long filters, then it might pay, instead of the convolution in the time domain, it might pay to go in the frequency domain and do a multiplication, and then by the FFT switch between those domains. But this is it. That's it. And let me give an example right away of the Haar example. So this is the example that's in Chapter 1. Chapter 1 takes this most basic filtering and goes all the way through the theory on to wavelets, which we will see in the second lecture because they're continuous time. But so the Haar example is just x of n goes to, the coefficients here are 1/2 and 1/2. And that's, of course, coefficients of a low-pass filter. So out comes y naught of n is 1/2 x of n and 1/2 x of n minus 1. And the low-pass coefficient, the high-pass coefficients have to alternate in sign because they add to 0 at DC, at 0 frequency. So y1 of n will be 1/2, using that 1/2 x of n minus 1/2 x of n minus 1. Okay. We average and we take differences. But of course, I'm still redundant, overdoing it because I've got 2 outputs now for every n. But now the downsampling term, why don't I just put in 2's here to indicate to take care of this one. Let's go to y naught of 2n. That would be, I just replace n by 2n everywhere, hoping that that is clear for you and for the video. So now I've done the total analysis step, the forward step. I'm only doing the forward step. I'm only getting from x to c, which are these numbers. These are the c's. These are these guys. Now, in this example, could you reconstruct the x out of these c's? Do we have a simple way to reconstruct the input samples, all of them, from the, so all million of them maybe, from 500,000 of these and 500,000 of those? Yes, clearly. In fact, very conveniently, we would just, how would we get x of 4 or something? We would add 1/2 x of 4 plus 1/2 x of 3 to 1/2 x of 4 plus minus 1/2 x of 3, and we would have x of 4. And how would I get x of 3 out of that? Just subtract, right? So actually, you might notice that those, in a way, that's almost like filtering. I mean, the reverse step involves filters that are not so different from the forward filters. But the main point is the information is there. Okay. But of course, Haar is very crude. It's like taking the inputs. So what's Haar doing? It's taking the input samples at discrete times, and basically it's taking them 2 at a time, those 2, and taking average and difference, taking the next 2, average and difference, the next 2, and so on. There's no overlapping. It's a 2-point DFT, really, also, equals 2-point Fourier, discrete Fourier transform. Just plus, this is the matrix, 1, 1, 1, minus 1 for the DFT. But it doesn't mean that this is, I mean, it's simple. So it doesn't capture all the possibilities, but it would actually give you some compression, because in probability, in all likelihood, we have a smooth signal or a smooth image, and x of 2n is probably very close to x of 2n minus 1. Those are neighboring samples here. So if we have audio, say, and the violin is doing its thing, then these two samples that are a split second apart are probably very close. And therefore, the average will be pretty near the sample, and the difference will be pretty near 0. If we just set all the differences to 0, so that would give us 2-to-1 compression, right? If we just ignored all those differences and kept the averages, what would that amount to? That would amount to every pair of points, every pair of samples we replace by their average. In other words, obviously we're giving up resolution there, and we would only want we would perhaps do that if the original sampling period had been smaller than, and we just really wanted to compress, and we're just willing to take averages 2 at a time. But we aim for better than that. We aim for better than that. But better than that is going to mean that this simple picture of no overlap, just block, block, block as a block transform, is going to go. Well, the block discrete Fourier transform could go from 2 points to 8 at a time. That's a possibility, important possibility. But that's not the wavelet idea. The wavelet idea is to have overlapping by using longer filters. These H0 and H1 will have more than these just 2 coefficients, and there'll be overlap. And let me repeat one particular filter, H0 and H1, that are of interest. The coefficients are 1, 2, 6, 2, 1. So that's a 5-tap low-pass filter, and I should divide by, what do those add up to, 3, 9? No, I don't. I didn't mean them to add. I know I'm wrong when they don't add up to a power of 2. Oh, it's minus 1s. Yeah. Now they add up to 8, which is a better number. Okay. That's a low-pass filter, right? The coefficients add to 1. And the alternating coefficients, which would be minus 1, minus 2, plus 6, minus 2, minus 1, add to 0. Yes, good. So that's a low-pass filter. And the high-pass filter is going to add to 0. And I'll divide by 4 to make that reasonable. There's a pair. There's an important pair. That's the 5-3 pair in JPEG 2000. JPEG 2000 is the improvement on this sort of block idea, and there are 2 filters in it. This 5-3 that I've written down up there, and then a 9-7 pair that's better. I just actually by email asked my friend at Los Alamos who worked on the FBI. So the FBI chose this particular 9-7 filter bank, and it's become the sort of standard in image processing, is 9-7. 5-3 is shorter, simpler, but not as, doesn't allow same compression. 9-7 is a little slower, of course, so we give up some speed for better approximation. and this is so this is the FBI choice for digitizing fingerprints. So it was in a way that was the first sort of real success for wavelets or for filter banks in open competition, because the FBI tried the old JPEG was an 8-point, or 8 by 8, of course, because it's 2D DFT. That was the old JPEG, and the FBI kind of expected to use it, but then their examiners couldn't identify quickly. One couldn't say, yes, that's, that fingerprint matches that from the output. It had lost the little things that in all our fingerprints distinguish us. The little, well, what do you know about fingerprints? Anybody? They're little. I'll just draw some fingerprints here. There's some dead ends in our fingers, and there are also some bifurcations where three lines meet, and also there are also little sweat. Now I'm really getting down to details here, but we're all born with little sweat pores that pin us down. So the wavelet results at the compression. Of course, everything depends what compression you ask for. If you ask for very little compression, well, everything can do it. And for images, 5 to 1, 8 to 1 is not asking much, and everybody could do it. But if you go up to 14 to 1, 32 to 1, and so on, then you really see who can survive so what does 32 to 1 mean? It means that we're throwing away 95% or 97% or something of these coefficients, effectively. 97% of the bits, anyway. So that's severe. And that leaves maybe only out of those 64 coefficients in an 8 by 8 block, we only have 2 left. If we're doing 32 to 1 compression, that was too much. The image is no good. But the wavelet image is pretty good if you make a good choice of wavelets. So we really have to understand. So in this standard, these two are the winners. So more and more hardware will be built to implement them. Of course, that's a major step. Any wavelet who lost that, I guess I'm speaking about it as a person, any wavelet that lost in the competition certainly a setback, because manufacturers are going to be concentrating on these. Okay, now, yes, sure, always.
Well, it's a few parts. The first thing is there a significance to the fact that, number one, that the low pass is 2 more than the high pass, and then also the addition of the 2 add up to a power of 2?
Well, gosh, that's true. That's yeah. Let's see what to say. And the fact that they're odd numbers. I mean, you'll see that I could this 5-3. I could create out of it a 6-2. The 2 would be Haar, of course. Anytime you see 2, the only thing with 2 coefficients effectively is Haar. Or I could, and I might reverse. Well, you haven't seen the reconstruction, but between the wavelet transform and its inverse, it involves a couple of filters too, and I could do the opposite order. So I could due to 6. And others, yeah. Hold on till you've seen a variety of the possibilities here. Yeah.
Yeah, but why is it, what's the significance of that?
That it adds up to,
And the fact that
yes, I guess that
you're
is,
choosing this odd number.
yeah, that's right. Yes, the significance is hidden in the details in a way. I don't think I can say in one sentence why these are winners, but I hope in 2 lectures to do it. Yeah.
Even number FIR filters rarely perform better than the next lower odd number one.
Is that right?
Might be part of the answer.
But why?
Yeah, that's,
I think because you lose some symmetry, maybe.
yeah, that certainly.
You still have symmetry, but you're sort of off-center.
Certainly, I wanted to emphasize that these are, as you see, symmetric filters. And for image processing, that's a very valuable property. If there are other filters, other wavelets, other filter banks that are not symmetric, I've mentioned the Dobeshy numbers, and those have a value. Those are quite efficient, but a little bit lopsided for image processing. So image processing has stuck to filters that are symmetric.
If you look at that at H0, it sort of looks like a little piece out of a sync function.
Yes.
Which is your classic band limited
Right.
function.
That's right. If I graphed that, it would look a bit like a sink. Yeah. It would look sort of as much like a sink as I could make it in with so few taps, or roughly. And it will have the property that it actually comes down to and hits. And in fact, it has a double zero here. It has a double zero. We mentioned, well, double zero for this chap. For 5-3. Of course, I have to tell you which one I'm referring to, because the 9-7 will have a quadruple zero. So I'll put, well, there isn't room to write that, but I'll write it anyway. Quadruple 0 for 9-7. It's the 9, actually, of course. Yeah. So that's really quite important. That the number of zeros at pi. This is as I hinted before. That's going to distinguish good ones from not so good. The number of zeros at pi, but why takes a little thinking. Okay, what do I do next? I've got these topics here. Perfect reconstruction. To explain that, I've got to do the inverse transform, right? And then I've got a second topic, iteration. Well, that's easy to explain. So let me deal with iteration right away. Iteration would say, okay, there we've come through the filter bank, got to these numbers. Hopefully and this is really a good way to imagine them as averages and details. So the average tells you what's happening in the whole block. The detail tells you within the block little fluctuations, which we hope are not too large. And now if I wanted to iterate, I would say, okay, I'll accept those details, but these averages, so now I have an average for every pair of samples, right? And so now I have a new signal, half as long. The average of each pair, I could say, okay, I'll find its averages and its differences. So I take this and send it through the same 1/2 filter bank followed by the downsampling, and the same difference filters followed by keeping half of those. So what's going to come out of that? Well, let's see. Yeah, maybe we can even figure out what comes out of that. So this is average of averages, right? We take, so we're going to like 4 to 1. We take the average of these two and the average of these two and average those. So what's the output here? For this Haar case, we can, where the numbers are easy, what are we getting out of that? I think, don't you think we're getting 1/4 of x of 4n and x of 4n minus 1 and x of 4n minus 2 and x of, in other words, the average of 4 guys with a 1/4 multiplying, right? That's what it would have to be. That's the average of this and its neighbor. And then the downsampling means I only want every 4th one. So I take the average of that and that. So that's all I've done here is the average. Now I'm taking the average of 4. The average of that and that will be the average of the 4, the average of the 4, the average of the 4, and so on. And then, of course, out of here, I'm getting differences on this grander scale. So that would be 1/4 of x of 4n and x of 4n minus 1 minus x of 4n minus 2 and minus x of 4n minus 3. This average minus that average. So it gives us like the fluctuation between this double block and this double block. So this is like more coarse details. These were fine details here. Fine details. And this would be a coarse average, a big average, say coarse. We're on a coarse mesh now because we're taking more than before. Have I done this picture correctly, or maybe these circles. Yeah, there's those circles, and each circle involves 4 values. So this is the average of that and that, which is the average of all 4, and this is a coarse detail, that average minus that average. You see how I can iterate the picture. This is the, let me draw the block diagram just because it's quite clear. Here's x, I'll just jump to y1 of 2n, y0 of 2n, the low frequency part, and then this is what we go to z0 at 4n, you could say, and z1 at 4n. So this is high, this is low, and this is high, and this is low, low, and this is high, low. And I'm not planning to work more on this, but I could. It's a free country. So you could imagine doing that too. Then we would be getting a matrix of 1s and minus 1s that probably it's associated with the name of Adamard. But this is this tree. Now we could continue again to 8 ends. So do you see, after 3 stages, our filters, they got a little longer. Because what's the filter that's producing this thing? What's the low, low, low filter that has greater length and is producing, out of this original guy, is producing this one in steps. Well, I guess it's 1, 1, 1, 1, 1, 1, 1, 1 probably, divided by 8 is the filter that's, if we wanted to do it directly from there to there, that's the filter we would use. So we're building longer filters by iteration, and better. We're sort of like, you could imagine this picture in frequency. If I imagine frequency 0 to pi, let's say, you could say that roughly the first stage separates out low frequencies from high frequencies with some imperfection because we don't have ideal filters here. And then the high frequency, we leave it. So I'll put yellow for that. Leave it. Now this one, we're iterating again, so we're sort of dividing this into low, low, and, oh, I don't know, I'm making a mess here out of this. Anyway, something like that. And this little piece here is there, and it's okay. We're doing a logarithmic chopping up of the frequency. And that's important, that it's logarithmic rather than uniform. What the standard filtering process has been with audio, the standard, making CDs or good audio, high quality audio, has taken the frequency thing and chopped it up into many, 512 little pieces. And, or modems, actually, a company called Aware in Burlington is developing modems. And there's a lot of interest. So I just heard a lecture about the DS, high speed, high bandwidth modems. I mean, what goes on there? There's certain frequencies that maybe coincide with radio transmission or something. So you chop the signal up in many pieces, many small pieces, and then some of those small pieces you use a notch filter that kills them, knocks them out, and interpolate, because if you try to send it that frequency, it's interfered with. Oh, it's an amazing world that some of you will know more about than I. Okay. So you see the iteration idea, and the logarithmic tree of iteration, of iterating on the low pass, which is the most common, but not the only possibility. Again, just to say. So in the end, you see how these add up to 1. We have 1/8 length here, and 1/8 length here, and 1/4 length here, and 1/2 length here, and those numbers add up to 1. So we're doing critical sampling, output length equal input length, and very efficient. But is it effective? Well, the Haar filter is not the best we could do. This is way better. This is, as Bob Nichols said, is much closer. The graph is much closer to ideal, but still not ideal. Okay, I'm ready to try the reconstruction step. What's the inverse transform? And I don't know where I'm going to put it, to tell the truth. I guess I better, this was the end of the analysis step. I better follow it by the synthesis step. So these are the C's. Okay, and let that stand for whatever process we may or may not do to the C's. Perfect reconstruction, I'm going to construct the inverse transform so that if we don't lose any information, we get it back exactly. Okay, so what do? Well, these vectors now are half length, right? So, and we're aiming for a full length vector. Let's say 1,000 samples went in. There's only 500 samples, 500 numbers, not samples. Oh, no. 500 numbers here. Well, we really want 1,000 numbers. So we just put in zeros in the odd positions. So we get to something, maybe, I don't know what, so that's called upsampling. Is put zeros in. And now we have, we upsample both of those. So this is like, obviously, just a simple operation, no hardware involved here to speak of. So now I'm getting something. Now I need a new letter. I've used X and Y. What about W of N? W naught of N and W1 of N. So what's W? W naught of N is either Y naught of 2N or 0. If it's even, if N is, oh no, I've got to say this correctly. It's either Y naught or 0. Can I say it just that way? You see what I'm doing. I'm just putting these zeros in to bring the vector back to full length to prepare it to go through another filter and another high-pass filter. And then I'll take these two outputs and add them and hope that and try to get X back again. That would be perfect reconstruction. That the output was the same as the input. Okay. So what do I have to do now? I've got to construct, if you give me these filters for the forward step, I'm hoping to be able to construct these filters for the reverse step to give perfect reconstruction. That's my goal. And in this Haar example, we could do it. But often it would turn out that if you just give me a couple of filters, a nice low-pass filter that you like and a high-pass filter that you like, I can go through the algebra and produce the inverse. I mean, you're really just giving me a matrix and I'll invert it. But most likely, if you just chose zero at random, the filters in the inverse will be infinite length. And we don't want that. If they are, we've lost speed and we've killed the whole idea. So the idea is perfect reconstruction while stay with FIR, stay with finite length. Okay. So we have to figure out the requirement. We have to figure out the requirement for perfect reconstruction. And I think I have to go through this bit of algebra now. Any discussion? Thanks for questions as I go. What I'm planning to do now is go through the algebra of what's the condition on these four guys that gives perfect reconstruction. And then I'll hope to satisfy that condition with finite length filters. And I can tell you how it happens. Let me put these numbers up here because they're quite significant. So I've told you the two H's here. Now I have to tell you the two F's. And you will see that this H is connected to this F by, if I flip signs, I get a low-pass filter. I divide by 4. And this low-pass filter is connected to this high-pass filter also by alternating signs. I think maybe I alternate. I'm now alternating what am I doing? Yeah, I'm alternating the middle, this one and this one, and I'll divide by 8. There's this connection here between, and you'll see why. So I'm really giving you this example as something to watch for in the algebra. In the algebra, we will discover that this H0 is connected to the F1 and the H1 is connected to the F0 by alternating signs. So that makes them special. Sorry? YR?
Why don't you alternate the signs?
Should I? And maybe I should have. My memory doesn't tell me. I could maybe I should have the negative of this, which would mean I'd alternate. Maybe I should alternate that one. Oh, what is that? What I did? Oh, sorry, I'm up here. What did I do? I kept that, alternated that, kept that, alternated that, kept that. But maybe I should multiply the whole thing by -1, which would involve rewriting. So now what have I done? I've now alternated, kept, alternated, kept, alternated, and it's one or the other. And you would think at my advanced age I could remember which, but should be +1. Good. Now you've got the whole picture now. All right. Okay. So could we? Yeah, it's kind of fun to say, how do we go through the algebra of this? Do we want to do it as big matrices? Probably you'll say no. And this time I'll agree with you. Frequency domain is better. So I have to figure out what all these steps do in the frequency domain. In came an x of omega. Now if I'm going to draw that, put that whole picture in the frequency domain. Okay. I'm going to try anyway. And let me put it above. All right, so right above the filter bank, so this is the analysis followed by the synthesis bank. I'm going to put this same thing here in the frequency domain, so my input is x of omega. And now I'm going to ask, what's my output y0 of omega? In the frequency domain, what do I have after no, I don't want an equals. I'm just following along here. Okay, so that's what I just erased is what went in. Yeah, let me put x of omega went in. Now tell me what came out of there. At this, I'm going to systematically follow through in a record 5 minutes the whole. I'll follow through the top channel, and then we'll just change zeros to ones, and we'll have the high pass channel. Okay, so you can all say it in unison. Here, what comes out after the first filter?
H of omega.
Times that. It's multiplied by h of omega, h0 of omega. Right, good. So now I've reached that stage. Now a little dodgy step, because I have to figure out what happens when I downsample. Is that going to be a multiplication by some function of omega? No. That's like important point that it isn't going to be that because this downsampling is not a time invariant, it's not a filter. It mixes frequencies up. It aliases. There's going to be an alias thing. And I'll tell you what happens here. And then I'll push forward. What happens here is that the frequency that's pi, that's different by pi, pops in at this stage because of this. Maybe we could see this. Give me two signals whose frequencies differ by, perfectly differ by pi. Well, I guess actually, DC, remember? Here's 0. So what's the signal that has totally 0 frequency? 1, 1, 1, 1, 1. And what's the signal that has totally pi frequency? 1 minus 1, 1 minus 1. Okay. And now downsample those. Take every other component. What do you get out of this? All ones. And what do you get out of this? All ones. So this step has introduced introduced these two frequencies, made them indistinct, mixed them up, aliased the process, and so what turns out is, for this, I'm now at this stage, there's the aliasing is an h naught of omega plus pi x of omega plus pi is what I've got, maybe times a half. Okay. So I'm sorry about that, but that's what happens. All right, now, oh, yes, actually, what I've done here includes both this downsampling step and the upsampling step. So I've actually reached, you'll be glad to know, I've reached there. Yes. All right. Now you're quite ready to tell me what the final thing will do, right? Because that's just an ordinary filter. So what do I have at the end of this channel? What's a filter do? It multiplies. It just multiplies by f of omega. So this is what I've got. There's a 1/2 way out. There's an f of omega that's multiplying both the signal we want and the alias that we don't want. So what's coming out of this channel has got this aliasing thing. Yeah. If I drew it in the frequency domain, which I may be unwise to try, but somehow the book does it. Somehow we've our original signal had some frequency description, and now we've popped in its alias. We've now got two little twins, and of course, if they don't overlap like that, we could probably, by sampling, sort them out. That's what Shannon's sampling theorem is about, that if I had one signal and it didn't overlap its alias, then I could reconstruct, but in fact, if the input signal has a lot of frequency in it, then it will overlap the other one, and right now I'm dead. And so one channel can't do the job. But what we can hope is that the second channel cancels the aliasing from the first channel, and then all this could be well. So let me just draw what's coming out of this. The second channel, of course, I'm just going to, it'll be, an F1 is the last guy, multiplying an H1 of omega, X of omega. That's what we'd like to see. And an H1 of omega plus pi, X of omega plus pi, which is what we are a little sorry to see. But now that's, so I've added because the end of the filter bank adds. So I've got to there. I've got to the output. Maybe I should call that output X hat. That's the output. Capital X hat. Okay. So what does it take for the output to agree with the input? I want this whole thing to agree with X of omega. is what I want, right? So what are the conditions? It's messy, but when you think about it, it's not that bad. We can identify the conditions very neatly here in the frequency picture. Okay. Yeah, we just look. We would like F0. Now, yeah, shall I write them in yellow? The two conditions. We have one condition that says that F0 of omega, H0 of omega, that's multiplying the true guy, and F1 of omega, H1 of omega, also multiplying the true guy, should be like 1. Or maybe there was a 1/2 out here, so maybe 2 is actually right. And now, so that's the, like, getting it right, getting the correct signal out. But what's the anti-aliasing condition? It says that whatever multiplies this alias should disappear. So that'll be an F0 of omega, an H0 of omega plus pi from one channel, and an F1 of omega times an H1 of omega plus pi from the other channel should equal 0. Right. So two conditions. Four filters, 4 unknowns, you could say, 4 functions to choose, 2 requirements, we ought to be able to do it. And of course, we can, and that leaves us a wide family of filter candidates to choose from. Not tremendously wide. Let me just say that it's absolutely possible and reasonable to have 3, 6, 8 channels going. So I have 8 H's. Now, what would the downsampling be like if I had 8? It would take every 8th component, because I would want every piece to have 1/8 of the length. Then I would have 8 synthesis filters, so 16 filters to choose, and probably not that many conditions. I'd have more freedom. But this, yes. Oh, so this is, but this is like a good case. Okay, now, can we make any headway on those in a few moments? How could I satisfy this second guy? Suppose I know the H's and I want to choose the F's. Suggest some F's that would do the job. Yeah, this is very important. Yeah, it doesn't even need that well in front of it, because it's, well, it is well. It's the right, yeah, so what is it? It's F, this guy matching who? This guy should agree with maybe this guy. So choose F0 of omega to agree with H1 of omega plus pi. Was that what you were going to say? Or whatever. I just want this darn thing to come out 0. Okay, but I've done half the job. What's the other half? What's F1? As H0 of omega plus pi. And now, but what little step do I still have to take? I've got to put a minus sign in, and I'm done. That only takes care of the bottom equation, right? So we could cancel aliasing. Whatever 2 filters you give me, we can choose the other 2 to cancel aliasing. But by no means have we guaranteed condition 1. So now we're ready to focus on condition 1, and now we're really down to the heart of the whole process. And I emphasize that this is now seeming relatively straightforward, but when Dobushi did it and found numbers, found these thing. She didn't do it this way, and it was people doubted it could be done and so forth. Okay, so now I'll put these choices into here. You don't mind if I I can play around a little. Let me see. For F, let me keep now. So I'm now going to settle on this. I'll keep F0 of omega. I'll make the two that I keep F0 of omega, H0 of omega, plus. Now what is F1 of omega? F1 of omega is, there's a minus. F1 of omega is minus H0 of omega plus pi, right? And what is H1 of omega? Oh, no, here. I'm trying to get 2, right? Let's just be sure I'm... Okay, so I'm following this line along. F0, H0, F1 I substituted this choice, and for H1 I'll substitute, you see, what's H1 of omega? From this plus pi, right? Because we're 2 pi periodic. So if I shift this by pi, then I shift this by pi. So there's an F0 of omega plus pi. That's great. This is it. We've got it down to one equation with 2 filters to choose. And luckily, it involves the product of those. So really, it only involves the product. I could say this is P naught of omega, the product of that. And this is a minus, and then this is P naught of omega plus pi. And that should happen to be 2. Okay. So now all I ask is to find some filters that solve that. So now, do you see the steps? Now that we've gone in this forward direction, but now to actually design filters, I'll go backwards. I'll choose a P naught that solves this requirement. So this is now the key requirement, and we have to look at it. Then, once I've chosen a P naught, I'll factor it into an F naught times an H naught. That'll solve this, that'll satisfy this requirement. Then I'll go to these that'll tell me the other 2 filters, and I've got it. Should I say that again? So we now have filter design. We could now be top speed design filters, design FIR filters. That's the wonderful thing. These are coming out finite length, provided we can get started. So tell me a filter that would do the job there. What would be a filter? It has to be anti-symmetric. Now that's, I'm sorry to see that.
Well, omega plus pi should be the same thing.
Yep, you're right. That left-hand side, if I change omega to omega plus pi, I'm reversing the signs. Ha!
Well, you've got to be a coupling conjugate. You've got to wipe out the
Right.
imaginary pi.
Right. Well, now here, so maybe it was okay now to realize that my right-hand side isn't quite a 2. Because I have to allow for the possibility that the output that comes back is a little delayed. I have to allow for the fact that the system might have delays in it, and it will have delays in it. Because if every filter I use only looks backward, and I use a bunch of filters, then somehow I'm not surprised if electronically, in real time, it's going to take, there's a little latency here. To get through the filter bank takes some time. The thing doesn't come out the instant it goes in. And so when I took Fourier transforms, what factor appears, because I just had x of omega here as output, but really it should have been what? e to the j omega L, which for consistency we'll call e to the I omega L. Right, so there's an e to the, no we don't, we will call it e to the j omega L. Right, okay, e to the j omega L. That's because of this L. So it wasn't a 2 after all, it was a 2 e to the j omega L. Or maybe actually, if I've done it right, there's a minus there. So if we're really getting it, so it's really 2 e to the minus j omega L. And now we're really got it. So let me identify what we've got here, because we really have reached the thing. Now, as was pointed out, this left-hand side is odd. If I change omega to omega plus pi, it reverses sign. So now what do I need here? If I change omega to omega plus pi, I want this should reverse sign. All that tells me is that L should be odd. L should be the latency is an odd number. You see that if L is odd, like 3, then when I change omega to omega plus pi, there'll be a e to the j 3 pi coming in, which will flip the sign just as the left-hand side is flipping. Yeah, don't lose. Yes. This is the true equation. So I cheated slightly by not pointing out this delay term before. That makes it odd, right? Let's go through that again. If that number L is odd, then an odd number like 3, then when I change omega to omega plus pi, everything stays reasonable. It stays okay. I change omega to omega plus pi, this left side flips, changes, reverses sign, and when I change omega to omega plus pi, the right side reverses sign. Because I'm multiplying by e to the minus j 3 omega. So e to the minus j 3 pi. That's the extra factor that came in. Now, what's going on here? We've got to this point by going full steam ahead here. The textbook chapter 4 will repeat those steps, but maybe the most important point for you to see is that they were perfectly reasonable. There wasn't. We just followed the rule here, and I didn't carefully go through that rule that involved the down to and up to bringing in the alias, but we had to skip past somewhere. Okay, let me give you an example of a p naught of omega that works. Can I just give you the coefficients of a p naught of omega? It's my favorite. -1, 0, 9, 16, 9, 0, and -1. That's a great example of p naught. Now, does it have this property? Sure.
When you downsample and upsample,
Yes.
does each step in the delay of L, or does only one or is it total?
Let's see. I don't know. Am I thinking that's where the delay of L enters?
And then L is an even number because whatever delay you get on one side.
Yeah. For me, the delay isn't there. This is this point where the aliasing comes in. Then the delay is because these F's are causal filters. They're lower triangular. That's for me. All these matrices are lower triangular, and when I multiply them together, I'm down below the diagonal. I'm 3 in this case. This this particular P naught has latency 3. It's do you see this? Can you see that those numbers work there? Now, how should I show that? I should compare. So these are the numbers that give me P naught of omega, and I'll tell you in the second lecture why I like them. Maybe let me just finish this lecture at the speed of light. Okay. All right. What are the numbers for P naught of omega? For P naught of omega plus pi? Well, that alternates. So the numbers for those are -1, 0, 9, -16, 9, 0, -1. You see that I alternated signs? And now when I subtract, what happens? Only this guy is left. The fact that these were 0 was the crucial point. The fact that these were 0 means, because they would have changed sign to -0, they did, but then subtraction, they didn't mess up. So there was only one odd-numbered component. That's it. One odd-numbered component. That's what P naught has to do. It has to do its job with only one odd-numbered component and otherwise zeros in the odd position. So here's the position 1, position 3, position 5, and it has to do its job with these zeros, because then when I do this subtraction, what would otherwise reinforce is 0. So only one term reinforces, and I got 32, so I should have divided by the whole thing by 16 to get 2. You see that this filter, there's a set of numbers, which is a filter, that is a great P0. And now if I factor P0 into F0, H0, which I'll do right after the start of the new lecture, then I'll get these. These are actually factors of I'm sorry. The factors are F0 and H0, not. So H0 is a factor. The other factor is F0. I claim that, yeah, here's a opportunity to do a multiplication in the break, or a convolution if you prefer. Take that polynomial with those coefficients, H0, and this polynomial 1, 2, 1, multiply them together, and hopefully you'll get P0. So that says that, yeah, this is a great filter bank. We've chosen numbers here so that the product is a P0, and this P0 satisfies this primary requirement of perfect reconstruction. There's the condition for perfect reconstruction. We could even start that multiplication. So, right, if I multiply a polynomial with those coefficients times a polynomial with those, so the constant term is what? I'm only going to ask you the constant term and the second term. So what's the constant term if I take that polynomial times this one? -1, right? -1 times 1. And what's the next term? 0. Right, 0, because -1 multiplies 2, and 2 multiplies plus 1, and together they give 0. And, of course, we could do the next term. -1 would multiply 1. That would be a -1. 2 would multiply 2. That would be a 4. And 6 would multiply 1 would be a 6. And we would get the 9. So we really do get this polynomial from the product of those. And if we started with this one, we could factor it into those. But now you actually, this lecture is running on far too long, but now create a 6-2 for me. Create a 6-2 for me. Well, I'll just factor differently. This is a 1-1 times a 1-1. So my 6-2 will be, I'll only keep I'll keep one of those factors there, and I'll multiply the other 1 by this one. So if I multiply that by 1, I think I get something like minus 1, 1. I think it turns out 8, 8, 1, minus 1. There's the 6, 2, whose product is still my same P0 that I liked so well. And this is a perfectly okay guy. You see that what I've done is I've taken 1 zeroth pi away from the synthesis step and popped it onto the analysis step. Well, did I want to do that? Not sure. That's probably 5-3 was better. In fact, if I've got so many zeros, I might want that to be in the synthesis. I might want to reverse the order and this be the analysis filter and this be the F0. But anyway, you're seeing the algebra that we've reduced to. So all comes down in choosing a P0, factoring it, and then you're home. So there's more. Yeah, I mean, you could say, well, look, just give me the list of coefficients. I don't need to know all this stuff. But you really could see there, I think, how the steps go, how this great fact of just a multiplication made that thing work. Okay, now I really will stop.